The backbone of modern heavy infrastructure and aviation relies entirely on a single thermodynamic blueprint. On one end of the engineering spectrum, we have stationary power generation. These are machines scaled to immense proportions, engineered with a singular focus, producing massive electrical output to power entire cities. On the other end, we have aerospace propulsion. The architecture tightens into densely packed, lightweight blades, designed entirely to accelerate air and produce forward thrust. Despite looking vastly different in scale and operating with entirely divergent end goals, both of these systems are physical manifestations of the exact same process, the Brayton thermodynamic cycle. To understand how engineers build everything from closed-cycle power plants to supersonic jets, we have to temporarily strip away the physical hardware, the rotors and the casings, and learn to read the underlying mathematical diagrams. This graph is a temperature entropy, or TS, diagram. It represents the ideal gas turbine cycle, establishing a bedrock theoretical model where we assume zero thermodynamic losses. We start with isentropic compression of air, a perfectly vertical line straight up. From there, we move into the combustor, adding heat isobarically, meaning the pressure remains exactly constant as the temperature rises. Next is isentropic expansion through the turbine, another perfectly vertical drop. Finally, the cycle rejects heat isobarically, returning to our starting state and closing the loop. The area enclosed inside this complete cycle is the mathematical representation of the engine's net work. That enclosed area is the theoretical maximum energy we can extract. It is a perfect baseline that the reality of physics will immediately begin to degrade. In reality, perfectly vertical compression is impossible. Internal blade friction inevitably generates entropy, visually skewing those lines to the right. Engineers measure this penalty using isentropic efficiency, evaluating the actual slanted expansion against the ideal vertical line to determine potential work loss to friction. When analyzing complex multi-stage turbines, engineers also use small-stage efficiency, sometimes called polytropic efficiency. This tracks those exact same friction losses, but isolates them across individual infinitesimal stages of the compressor or turbine rather than the machine as a whole. Losses don't stop at the blades. The combustion chamber also introduces pressure drops. Pushing air through fuel injectors requires force, causing friction that drags the top boundary of our cycle downward, severely narrowing the engine's operating pressure ratio. The physical consequence of these combined thermodynamic losses is a severely shrunken net work area. To extract enough power to justify the fuel cost, engineers are forced to design complex mechanical interventions to claw back that lost efficiency. When the goal is stationary power generation, engineers deploy 3 specific modifications to maximize rotational shaft work over all else. The first method is regeneration. Instead of venting exhaust out of a stack, a heat exchanger captures wasted thermal energy to preheat incoming air. By transferring enthalpy back into the system, the combustor requires significantly less fuel to reach its target temperature. The second method is intercooling. Here, the air is deliberately cooled halfway through the compression cycle. Colder air is denser and easier to squeeze. By dropping the temperature mid-compression, engineers drastically reduce the physical work the compressor demands from the turbine. The third method is reheating, adding a second combustor straight between the high and low pressure turbine stages. Adding heat mid-expansion forces the gas to keep expanding, widening the TS diagram's right side and forcing more rotational work out of the turbine. These concepts form the architectural basis for massive open and closed-cycle gas turbine plants, and they make modern cogeneration possible, where electrical power and usable industrial heat are produced simultaneously. These heavy, stationary modifications are the ultimate tools for extracting maximum rotational energy. They deliberately leave as little kinetic energy in the exhaust as possible, but in aviation, the engineering goal completely flips. You want to extract only enough rotational work to keep the compressor spinning, intentionally leaving maximum enthalpy in the gas. Instead of turning a heavy generator shaft, excess high-pressure gas is funneled through a converging nozzle, violently converting thermal energy into sheer kinetic energy. This baseline architecture, compressor, combustor, turbine, and nozzle, is known as the simple turbojet cycle. But aerospace engineers make precise trade-offs based on speed. A turboprop extracts more mechanical power from the turbine to spin physical propeller blades. This moves a massive volume of air at a slower velocity, offering excellent efficiency at lower flight speeds. Pushing towards supersonic flight speeds requires a different, totally extreme architectural approach: the raw power of the ramjet and the pulsejet. These designs completely eliminate the mechanical compressor and turbine, relying purely on the aircraft's extreme forward velocity to compress incoming air. The architectural choice between a turboprop or a ramjet is dictated entirely by balancing mass flow rate and exhaust velocity against the intended mission speed. To evaluate these propulsion architectures, we rely on precise mathematical definitions of efficiency. Overall efficiency is determined by multiplying thermal efficiency and propulsive efficiency. Thermal efficiency measures how well the engine converts fuel energy into kinetic energy, a direct reflection of the Brayton cycle. Propulsive efficiency measures how effectively that energy becomes useful forward thrust. This introduces a strict engineering penalty. If your exhaust velocity is too high compared to your aircraft's speed, you leave massive kinetic energy wasted in the air behind the engine, plummeting your propulsive efficiency. Overall efficiency is the master equation. It proves that a successful aerospace engineer must perfectly match the internal thermal mechanics of the engine with the external aerodynamics of the mission profile. We have scaled from the theoretical perfection of the ideal gas turbine out to the complex realities of intercooled power plants and supersonic ramjets. Whether the primary output is turning a massive generator shaft to light a city or violent propulsive thrust to break the sound barrier, the laws governing the air inside do not change. Mastering applied thermodynamics requires recognizing that industrial generators and jet engines are simply different mathematical solutions mapped onto the exact same diagram.